Well, aloha everyone. Today we're going to talk about momentum. Now, what do we mean by momentum? Well, momentum has a very specific definition. We're going to use a lowercase p for momentum because m was already taken by mass. And p is going to be equal to mass times velocity. It's pretty straightforward. It's a very simple equation. Multiply mass and velocity and you get momentum. Okay, there's one thing else that we need to be careful of, and that is velocity is a vector and momentum is also a vector. So the direction of the velocity is always the same as the direction of the momentum. Pretty straightforward, not bad. Just means that you need to be careful about direction. In the case that the velocity is negative, the momentum will also be negative. If the momentum's in the y direction, the velocity is also in the y direction. Okay, so now that we have that, let's take a very quick example. Let's imagine that we have a car here. This car has a mass of, I don't know, let's make it 500 kilograms. And let's say it's moving this way at 2 meters per second. Well, again, remember, since we have to care about direction, be careful, decide which way we want to call positive. I'm going to call to the right positive just to make things easier. Could you call left positive? Sure. Then you'd have a negative momentum and a negative velocity. But since I chose right positive, I'm going to have positive momentum as well. Okay, so the momentum of this car is equal to, well, the mass is 500 kilograms times the velocity is 2 meters per second, and it's in the positive direction. So the momentum is equal to 1,000. And what are my units here? Well, it's a kilogram times a meter per second. So it's kilogram meters per second. Is there a special name for that unit? Unfortunately, not. We have decided that this one's just going to say kilogram meters per second. But if you want to start calling them Williamsons, maybe we can catch a trend on. So momentum by itself is pretty straightforward. But there's another thing you need to know that's closely related to momentum, and that is called impulse. And impulse is going to be equal to, we're going to use capital J for that. Sometimes you'll see a capital I. It's interchangeable, capital I or capital J. And J is going to be our impulse. It's also a vector. And that is going to be equal to a force times a time. Force times time. Again, impulse is a vector, so you need to be careful about directions. It might have a positive or negative, or if it's two-dimensional or three-dimensional, you need to take those directions into account and angles and all that, and components in the x and y. But here we have impulse is equal to a force times the time. So let's say that you put a force on an object. Let's imagine there's a box here, and we're going to put it on a floor that is frictionless. So if we have a frictionless floor here, you're here, and somehow you have super grippy shoes that can grab that frictionless surface, and you are going to push on this. So you're going to put your hands here, and you're going to push such that there is a force this way. Maybe the force of your push is equal to, I don't know, how about 20 newtons? And you do this for a time of, I don't know, how about 5 seconds? Well, how much impulse did you deliver to that box? Well, J is going to be equal to its force times time. Again, I need to think about my positive and negative. I'm going to call to the right positive again because that's the way we're pushing things. So J vector is going to be equal to, the force is 20 newtons times the time is 5 seconds. 20 times 5 is 100 newton seconds. All right, well, that's a little bit weird of a unit. You might remember that a newton is a kilogram meter per second per second. We're multiplying that times a second, which means that this second and the squared is going to cancel, and we're going to get kilogram meters per second as our units, which means that impulse and momentum are closely related. Now, when we say impulse and momentum are closely related, what does that mean? Well, it turns out that just like work and energy were closely related, because work is a change in energy. Work causes a change in an object's energy. The same thing is true here. Impulse is going to be a change in an object's momentum. So right now, this ball has 0 momentum. That can change, though, if I put an impulse on it, a force for a certain amount of time. Well, force times time is impulse, but impulse causes an object's momentum to change. So if I put an impulse on this object, now you can see that it has momentum in the direction that I put an impulse on it. So here I have 2 dynamics cards, one red, one blue. And you can see that it has this plunger with a spring on it. So if I compress it like this and then push this little button, the energy is released. Okay, so I'm going to put these 2 things together. I'm going to compress this one to about level 2, which is right there. And I'm going to put these 2 dynamics cards together like so. When I push this, you can see that both of these move apart at about the same speed. And the reason for that is because of 2 conservation laws. The first is the law of conservation of energy, which says energy cannot be created or destroyed, which means the energy that we start with has to be equal to the energy we end with. In this case, the elastic potential energy that I gave this system by compressing the spring has to be equal to the kinetic energy of the system afterward. But they move apart at about the same speed for another reason, and that's called the law of conservation of momentum. Conservation of momentum says whatever momentum you have at the beginning is equal to whatever momentum you have at the end. The total momentum of the system does not change. So, because of that, if they're sitting together like this, if these 2 cards are sitting like this, it's very easy to see that the total momentum of this system is 0 because the velocity of everything is 0. But afterward, the total of the momentum of the system must remain 0. So when I let these 2 things go, they're moving, which means that there's momentum in the positive direction, and there's also momentum in the negative direction. Since they're about the same mass, they have to move at about the same speed in order to have about the same momentum in the positive and negative directions. Meaning, the positive momentum cancels the negative momentum, and the total of the momentum of the system, even after this going apart explosion thing, has to be 0. So now I'm going to change this experiment a little bit. I'm going to put this back to 2 again. We're going to put these 2 things together. Only this time, I'm going to give this object a lot more mass. Like so. Now, the law of conservation of energy still says that the elastic potential energy here is going to turn into kinetic energy that is shared between the 2 objects. However, the law of conservation of momentum now says the total momentum of the system before and after has to remain the same. So before, again, we have 0 momentum. When I trigger this, you can see it changes quite a bit. This one shoots off pretty fast. This one barely rolls. Why is that? Well, because it has a larger mass, the momentum of this object, m times v, has to also equal the momentum of this object, m times v, in the positive direction here, in the negative direction here. So because of that, this one has a large mass, so it needs to be multiplied by a small velocity. This one has a small mass compared to that one, so it must be multiplied by a larger velocity for those 2 momenta to cancel again. Remember, the total momentum of the system has to stay 0. So if there's a large mass, there's a small velocity. If there's a small mass, there's a large velocity. So in the case of the 2 carts, here they are, 1 cart here and 1 cart here. In this case, when we had these 2 carts, the equal masses were going in opposite directions. So let's say that this was going at, I don't know, about the same speed of, I don't know, how about half a meter per second. So this v was equal to 0.5 meters per second. This v is also equal to 0.5 meters per second. This is the after picture. What did the before picture look like? Well, we had our before, and it looked like this. We had one cart here, one cart here. I guess they're a little bit closer to center. Let's move those. There we go. And they were not moving. So what is the total momentum before? Well, it's 0 kilogram meters per second. Because nothing's moving. All the velocities in that case are 0, which means all the momentums are 0. What about here in the after picture? Well, in the after picture, one of them is moving right, one of them is moving left, which means we need to pick a direction, and actually we need to be consistent throughout the entire problem. So throughout the entire problem here, I'm going to call to the right positive, which means that this velocity here has to have a negative sign on it. Okay, so what's the total momentum at the end? Well, you can see here that the total momentum, it's going to be equal to the mass of car 1 times, let's call this one 1, let's call this one 2, that's 1, that's 2. Okay, so it's going to be the mass of 1 times velocity 1 plus mass of 2 times velocity 2. Now, it turns out that these two velocities are the same, just one is positive and one is negative. It's also true that these two masses are the same. So because of that, this product, negative 0.5 times whatever the mass is, and this product, 0.5 times whatever the mass is, are going to cancel. And because of that, this entire thing, so it's going to be negative 0.5 meters per second times m1 plus 0.5 meters per second times m2. m1 and m2 are equal, so that means this and this are the same thing, just one's positive, one's negative, which means that they're going to bam, and we are left with a total momentum of 0 kilogram meters per second. So what about the case where one is a lot more massive than the other? So before again and after. So the before picture looks like this. We have one car there, one car here, and we have a whole bunch of mass on top of this one. And the other car has no mass on it. And we're going to put these together, so like so. There's my before picture. And it's easy to see again that the total momentum before is going to be equal to 0 kilogram meters per second. Afterward, what's going on? Well, this one is going to be going this way slowly. And it's got a whole bunch of mass on it. And this one is going to be going, we're going to pretend that those look the same. This one is going to be going this way fast, but it has a lot less mass. So what is the total momentum? And let's call this way positive. Really doesn't matter. The total momentum is going to be equal to, well, it's mass of 1 times v of 1, and let's call that number 1. Let's call this number 2. That's 1, that's 2. Mass of 1, velocity 1, plus mass of 2, velocity 2. Well, we know that mass 2 is smaller than mass 1, so that one's smaller. But we know velocity 1 is smaller than velocity 2. We know mass 1 is bigger than mass 2, and we know that velocity 2 is higher than velocity 1. So because of that, we have a small number, a big number times a small number in the negative direction. So negative, I shouldn't put the negative like that. It's wrapped up in the velocity, right? So this velocity we know is negative. So we have large times small plus small times large. One's negative, one's positive. These numbers are going to end up multiplying to the same thing, Just one of them is positive, one of them is negative, which means that the total momentum in this situation has also got to be 0 kilogram meters per second. Proof that the law of conservation of momentum is true. So let's try another example here. Let's imagine we have a ball, and this ball is rolling this way. Maybe it's going at 3 meters per second. This is my before picture. And afterward, maybe there's going to be some dude over here, and he is going to, he's waiting up here. And what's going to happen is this guy is going to kick this ball. So this ball is going to, he's going to kick it, and afterward, the ball is going to be rolling this way, I assume. And let's say that the force that he uses is going to be equal to 100 newtons. And let's say the time that he is in contact with it is, I don't know, 1/10 of a second sounds reasonable, 0.1 seconds. And let's make the mass of this ball 100 grams or 0.1 kilograms. I want to know what is the final velocity of the ball. Well, in order to calculate that, I need to think about the law of conservation of momentum, which says the momentum you start with has to be equal to the momentum you end with, unless that momentum changes due to impulse from outside the system. So I like to write it this way: Pi, initial momentum, plus J, which is impulse, is equal to Pf. And in theory, these are lowercase p's, so make sure you're writing them as lowercase p's. Okay, so Pi plus J is equal to Pf. So the momentum before, well, that's got to be in this picture up here. What's moving in that picture? Well, it's the ball. So it's going to be equal to the mass of the ball times the velocity of the ball at the beginning, so V initial for the ball, is plus, well, now it's impulse. Well, we have a force and a time, so it's going to be force times time. Don't forget that these things are vectors too. Being a little bit sloppy with my vector signs there. So force times time is equal to, at the end, it's also the ball moving. It's going in the opposite direction, which means we need to be careful about signs. But it's going to be mass times velocity final of the ball, vector. All right, let's choose, I don't know, to the right being positive again. In that case, this 3 meters per second at the beginning needs to have a negative sign. Okay, so let's see here. We're finding the final velocity of the ball, so I'm going to divide by the mass. So mass of the ball times V initial of the ball, vector, plus force times time, vector, divided by the mass, is equal to V final for the ball, vector. Okay, so when we do this, let's plug in some numbers. The mass of the ball was 0.1 kilograms. So 0.1 kilograms times V initial of the ball. It started moving at negative 3 meters per second, plus, what was the force he used? It was 100 newtons times a time of, he was in contact with the ball for 1/10 of a second, so 0.1 seconds, all divided by 0.1 kilograms should be equal to V final for the ball. Okay, let's see what we get. Grab our calculator here. Probably don't even need it. But 0.1 times negative 3 plus 100 times 0.1. That much gives me 9.7. Oh boy, I don't know if I like where this is going. Divided by 0.1 kilograms, it's going to be 97. Boy, that was a heck of a kick. So V final for the ball is going to be equal to 97 meters per second. That's ridiculous. way too much. I think I used way too much force on that. But yeah, there you have it. That's how you do a problem like that. So that's really all there is to it as far as momentum goes. Remember, be careful of your directions. If you're working in 2 dimensions, you're going to have to break it into components in the x and y and solve them separately. Be careful about that because sometimes you'll have to do that. In any case, mahalo for watching and see you next time.